So stay with me, please. Continue. Um, so let me stop share and do a poll. So partly by way of announcement, Monday is a holiday, it's Memorial Day, and so we will not be meeting for class. So I'd like it if you're aware of that fact so that you're not sitting here lonely on a Zoom waiting for me. Then I'm just interested in how you're thinking about the pace of things so far. We got out early on Monday. We'll probably get out early again today. The time consuming part of class will be things where we'll have a quiz or an exam, and I'll be, interacting with you online, and that'll take a little more time than simply presenting material. So I just wanted to get a sense of how you're feeling about things so far, because I know summer classes, can feel overwhelming, or it can feel manageable if you're in in the right state of mind, the right frame of mind for things. So couple of more responses would be very cool. All right, so seems that we are aware for the most part. If you were not aware that Monday is a holiday, be aware now. I'm glad that not too many people are feeling like too much too fast. I've taught this class many times in the summer. Every now and then I'll see a reminder that I've left myself where I've started class at 9 o'clock in the morning, and we went until a natural breaking point and then gathered again in the laboratory. And one of the students never came back from break, never came to lab. And then I checked my roster and they had gone and withdrawn from the class already. That happens sometimes. I hope that you're not feeling that overwhelmed that you would pull out of the class. So I want this to be a successful endeavor for you. You're taking time and money in the summer to take this class, and I want you to succeed and do well. And we'll need to balance, your workload and your pace, and kind of identify places where you are like, oh, wait, I need to find a tutor for this because this is more than I'm prepared for right now. So give you a little chance to find out if that's you. And then, wow, we've got 3 people with their niece weirdly getting married in New York. Lab is going to be asynchronous. My original plan, was to have lab in person. So I scheduled it synchronously, and then it's insane how early I have to schedule things. So spring 2022, so after the fall semester and it becomes January, that is the spring 2022 semester. I had to schedule that a year and a half ago. So when this summer schedule was due from me, there was different guidance on COVID restrictions, and as a department, we made a decision that we would have the chemistry labs in person as much as we could, because the chemistry lab experience is really, it's more technical, hands-on something. And then the lab experience the lab experience for physics is something we can manage online. So we have the physics labs online. So a few of us are going to our niece's wedding this weekend, and some couple of lucky ducks are doing something actually fun. Some people are working, some same old, same old. All right, I will stop sharing results and I will return to the chat to check things out. So lab, if you go to the Canvas page, which I must have somewhere. Oh, they make me so mad. Hold on, let me move this up here. And then find Zoom again. Share screen. So as much as possible, if I can find decent online simulations for lab, I do that. And so this first lab is a little bit lame, but the idea is that we're just gonna take a peek at what's going on with the slope of a line. And so if we can set it through 0 and then set a place for, maybe this isn't the one I want, maybe this is the one I want. Set another place on the line, then what we have is a line with a slope y equals mx plus b. M is the slope of the line. And if this were a graph, I mean, this is completely unlabeled, undefined here. It's just x versus y. But if this was a graph of position versus time, then the slope of the line would represent the velocity. Slope is rise over run. And so if the rise, if the y-axis component is distance in meters, and the run, the x-axis component, is time in seconds, then the slope of that line is meters per second. Whereas if this was a different kind of graph, if this was a graph of velocity versus time, then the y-axis velocity would be meters per second, and then the x-axis time would be seconds. Oh, come on, chat, where did you go? So meters per second is going to be, meters per second is acceleration. This course, PHS 211A, is a 4-credit class that includes lecture and lab. I have the ability to set up a separate Canvas page, but I figure that's a pain for everyone. So it's lecture and lab together in one class. If you look at the whole boring syllabus and scroll down a bit, you get to the part where the grade comes in. 15% of the course grade is the homework. The homework, you can get full credit by doing those same homework problems over and over again until you have them correct. 20% of the course grade will be quizzes. Quizzes are the quizzes that, I know everything's labeled a quiz, but you know, the things that I specifically list as a quiz that you do. So next Wednesday, we have a quiz on chapters 1 and 2 material. It's kind of like a mini exam, but it's only a quiz on a very small number of chapters. I will mention, we have pretty much a quiz or an exam each week. That makes me different than the other Dr. McTaylor who's teaching general chemistry right now, who has a quiz or exam every single day. I think that's a little bit much. She thinks it's pretty cool. So we just, there's a slight difference there. Lab is part of the course. You have to pass lab in order to pass the course. Really and truly, lab should bring your grade up, at least not bring it down. The labs are pretty, they're not terribly difficult. I'm not asking for a 5-page paper and a ton of calculations, just some simple follow these directions and interact with something. Move the dots around, place the components somewhere such that you're seeing something behaving in a certain way. I had dreams of like a series of labs where you're taking a ball and tossing it around and doing something, and collecting data that way seems a little too difficult to expect people to be able to have all the tools and do that. So I decided not to go that route. Most of them are just online simulations. Participation, my very first semester teaching things online was the spring, or this course at least, spring 2020, where we didn't come back from spring break and the rest of the semester was online. And there was a whole lot of debate, should we do synchronous online, asynchronous online? How should we do this? I am now, a year's worth of experience fully believing that synchronous online is way better than asynchronous online for most people. And I just want to keep you engaged. If you get disengaged, if you walk away, if you don't do any work for a week or two and then try to come back into it, it's so much harder. So it's my hope with just regular check-ins on participation that are a part of your course grade that I will encourage you with a pretty low bar. It's not hard to do, to just stay engaged. And then we have exam 1 on chapters 1 through 5 and exam 2 on chapters 6 through 10. And you put them all together, and I hope that adds up to 100%. I think it does. So that's the plan with that. So no separate page for lab, because I just don't think there's a great reason to do that. And our schedule, I will try my best to stick to the schedule. We do have a quiz on chapters 1 and 2 material during class time next Wednesday. Next Wednesday, we'll be finishing up chapter 3. We're going to start chapter 3 today. Next Wednesday, we will finish up chapter 3 and then have a quiz on chapters 1 and 2. I'll ask you to do that here live in person during class time, where I am able to be with you on Zoom chat. If you have questions that you're like, wait a second, I'm not quite sure what you're looking for on number 3 here, I can tell you. I can give you a hint. I can make an announcement to the whole class if it rises to that level. But if it's just something where you were a little bit confused and you want to ask me about it in private Zoom chat, I can do that, and it won't be disruptive to everybody. So there's that plan. So we have a quiz there, and then the following week, Wednesday, June 9th, we have another quiz, this time on chapter 3 material. But then when we get to week 4, that day that would have been a quiz will now be exam number 1 on chapters 1 through 5. I'm a little bit in denial. I haven't quite figured out how I'm going to do everything This summer, one of my jobs is as the department chair, and the provost, who's like my boss's boss, has called a meeting for on some of these days. And so I need to figure out the best way to manage things such that I'm not missing an important meeting, but I'm not shortchanging you guys. So I think on some of these days, and I will let you know which ones as soon as I kind of figure it all out. On some of these days, I will be having class be asynchronous. I'll have a lecture video that I will post for you to watch and check in with you, but we won't actually be here together on certain days. And so I'll let you know which ones those are going to be. And then I'm always willing to help you out in any way I can if you have questions. All right, so what do I want to do? I want to find this. Give me one moment to get things organized here. Here we go. Want to go over a couple of things just to review a couple of points and make, just do some examples because I think it's helpful to work through some examples. I encourage you, forever like working through examples, if you have a calculator handy, and I hope you do, to pull out the calculator and try to run through the calculations at the same time that we're doing them, so that if you get a different answer than I do, maybe you're right and you can point that out to me, but maybe you made some kind of mistake there, and you can be like, wait, when I plug this into my calculator, I'm not getting the same answer as you. What's going on? And you know, can avoid problems like that. So we have 4 equations of kinematics. The equations of kinematics deal with the kinematic variables. There's X in meters, and that stands for displacement. That's the change in position of something. We have V naught, a V with a little 0 after it, which stands for, oh, I guess I didn't want to do an equal sign, stands for the initial velocity in meters per second. We have V without the little 0 after it. That's final velocity. That too has units of meters per second. Why would velocity be changing? Well, because of acceleration. That's the A, meters per second squared. Acceleration is a little bit weird, as is displacement X, a little bit weird, because if we're talking about something in the X axis, then I would have to tell you the acceleration, or maybe it would be something we'd be looking for while we're solving the problem. Whereas in the y-axis, here near the surface of the Earth, on planet Earth, we have this acceleration that's already given to us. The acceleration due to gravity here on Earth near the surface of the Earth is directed downward, that's the negative sign, negative 9.8 meters per second squared. That's a very specific acceleration that we have here on Earth near the surface of the Earth. And then time in seconds is another of the 5 kinematic variables. We have 5 kinematic variables, 4 kinematic equations. We need to know 3 of the unknowns, 3 of the variables, in order to solve for something else. And so we have a car moving at a constant velocity of 25 meters per second straight east. What is its displacement 4 minutes later? There's not as much opportunity to draw pictures in an online class as there is in person. But I encourage you to draw the picture and to not be ashamed of your artwork, because you cannot possibly be a worse artist than me. This car is traveling at 25 meters per second. When we encounter it, that's a 0, 25.0 meters per second. When we first encounter it, and it will continue traveling at 25 meters per second for as long as we know anything about this car. So we already know the initial velocity is 25 meters per second, and we know the final velocity is 25 meters per second. And if we know those things, we know that the acceleration is 0 meters per second squared. We already know a whole bunch here, but that's not going to help us get to the answer. We do have to know 3 of them, but 3 will be important. What is its displacement 4 minutes later? Well, I have velocities in meters per second. Acceleration is always in meters per second squared. Minutes is not seconds. I need to convert this. So 4 minutes, I guess I'll do MIN. I know this equivalency. I want to cancel out minute. So I want minute in the denominator. 1 minute is 60 seconds. So minutes cancels, and 4 times 60 is 240 seconds. All right, so what do I know? What don't I know? What don't I know? The only thing I don't know is displacement. I have every other kinematic variable accounted for here. So what I can do is, I guess I'll go to the scary equation and hopefully do no harm. You don't take the Hippocratic Oath as a physics professor, but maybe you should. X equals 1/2 V naught plus V times time. What this means, the 1/2 V naught plus V, is the average velocity during the time in question. Because the car started at 25 and finished at 25, I could plug in those numbers. 25 plus 25 divided by 2 is 25. Or I can say that the other version of this same equation, if the velocity isn't changing, is X equals VT. That's another legitimate equation if the acceleration happens to be 0, which we figured out that it is. So, hey, this is an easy question. So it's moving at 25 meters per second for a time of 240 seconds. We don't have a ton of weird algebra we have to do or anything. So 25 times 240 is 6,000 meters. If I want to be careful with my significant figures, it looks like I have 3 sig figs here. What, 2 sig figs in the 4 minutes? Maybe I would say x equals 6.0 times 10 to the third meters, or if I wanted to be that way, I could say x equals 6 kilometers. I would tell you on a quiz or an exam what I'm looking for an answer. And another of the shortcomings of Canvas is that it's not equipped for scientific notation. So on a Canvas quiz, I might say, express your answer in kilometers. And then you would go to the bottom answer there. Otherwise, I would just say, tell me your answer in meters, and typing 6000 would be the best way to put that into Canvas. And that would make sense. Another thing, I hope you're listening. I don't know what's going on. Question?
Yes. Can you just clarify how you took the initial equation, the x equals 1/2 times the Vought v times time, and made it into the x equals v times t?
Sure. So what we figured out here, this car is moving at a constant velocity of 25 meters per second. So that means that the initial velocity was 25 and the final velocity was 25. That's the definition of constant velocity, that it's not changing. So this equation is just a little too cumbersome for the task at hand, right? Because it's giving us this definition of average velocity, which is really good if the velocity is changing, but it's just kind of lame if the velocity isn't changing. Because I'd say 25 plus 25 is 50, divided by 2 is 25. So this equation turns into x equals vt. Maybe if I did a little bar over the v, that would indicate average velocity. X equals average velocity times time, and the 25 meters per second is our average velocity in this case.
Oh, okay. Thank you.
You're welcome. Right. Clear all drawings. Okay. Now, I'm gonna find myself. I toss a ball straight up in the air at an initial velocity of 15 meters per second. How high does it go? So I'm standing here. My leg isn't attached for some reason. I'm going to toss a ball straight up in the air. I've done this before in my life. I don't know if you've ever tossed a ball straight up in the air. If you toss a ball straight up in the air, it goes up until it stops going up, and then it starts coming down again. So at some point, it reaches some maximum height, and that's kind of what I'm interested in. Y max, I guess I'll say. So I want to know what its maximum height is when I toss the ball up with an initial velocity of 15 meters per second. And I don't state it explicitly, but you can assume that I am here on Earth such that there is the acceleration in the y-axis, which is the acceleration due to gravity, which is directed down in the negative y-axis and has a magnitude of 9.8 meters per second squared. All right, so I stated it, but I didn't make it clear. I'm going to toss the ball up. The initial velocity is 15 meters per second. And then it's going to slow down. And then it's going to slow down. And then it's going to slow down. And then eventually it's going to have a velocity of 0 meters per second instantaneously. That's m per s. I'm having trouble drawing here. V equals 0 meters per second at its maximum height. After which it starts having a negative velocity. So it has a positive velocity the whole time it's moving up, and then it has a negative velocity, negative y-axis coming down again, negative velocity the whole trip back down. So, known and unknown. What do I know? What don't I know? I know the initial velocity is going to be positive 15 meters per second. That's positive y-axis. This is one-dimensional kinematics, so I don't need to stress out about making it clear which axis I'm in, because we know we're just talking about y-axis motion. I know my final velocity in the y-axis right now is going to be 0 meters per second when at its maximum height. So y max. I don't know what it is, but I know when I'm going to be there. And I know that my acceleration is the acceleration due to gravity, negative 9.8 meters per second squared. What I don't know and don't care about is time. This question is asking how high it goes. I don't know if there's anyone in the class who doesn't have English as their first language. And in a way, it kind of doesn't matter whether English is your first language, because physics may not be your first language. If you don't understand what a question is asking, that may be my fault for not being very careful with choosing my words. I know it can be awfully confusing, and I don't mean it to be. That isn't the point of the course, figuring out what the words in the question mean. So if you're ever like, wait, I don't know, how high? Hi, what do you mean, high? Let me know that, you just have a question about what I'm looking for there. So high, I'm looking for the maximum height, the maximum y-axis displacement. There's other ways of phrasing that may be more clear depending on where you're coming from. So feel free to ask questions about that. That's not the point of the course, and I will try to be careful. I just banged these questions out right before class started and wasn't really in the mode of being as clear as possible. All right, so I don't know the time and I don't care about the time for this question. I'm looking for the maximum y-axis displacement, which in our kinematics equations right here, displacement is represented by x. And acceleration, we're going to replace with the acceleration due to gravity. So I am looking for an equation of kinematics that doesn't have time in it, because I don't know the time and I'm not looking for the time. If I didn't know the time, but I was looking for it, then I need an equation that has that variable t in there to be able to solve for that variable. But I'm not looking for time, so I don't want that variable there. And I don't have a number to plug in for time. Nobody told me that this took 10 seconds or 5 seconds or 3 seconds. So I don't know what number I plug in. So I want to find an equation that doesn't have time in it. This equation, V equals V naught plus AT, has time in it. So that's not good for me. This one has time in it. It's not good for me. This one has time in it all over the place. What a mess. So I'm left with V squared equals V naught squared plus 2AX. And what I'm looking for is X, or really Y, right? So if I wanted to rewrite this same equation for what we're doing, I'd say V squared equals V naught squared plus 2. Instead of A, we're using the acceleration due to gravity G. And instead of looking for x-axis displacement, we're looking for y-axis displacement. So I could rewrite the equation with the variables appropriate for what we're doing. Right, so I need to do some algebra. I have a cousin, he's a little bit older than me, and he went back to school a little bit later in life, and he was taking algebra and emailing me on a regular basis for a little help and encouragement. And I kept telling him, algebra is your friend. And I don't know that he ever believed me, but I want you to believe algebra is your friend. Let's have some fun with algebra. First thing I'm going to do, I'm going to subtract V naught squared from both sides of the equation. V squared minus V naught squared equals 2GY. I did that because I'm one step closer to getting Y all by itself if I take this V naught squared and subtract it from both sides of the equation. Then I'm going to divide both sides of the equation by 2G. And now I have Y all by itself. It doesn't matter if Y's on the left side of the equal sign or the right side of the equal sign. So long as it's all alone by itself on one side of the equal sign, that's perfectly sufficient. So Y equals V squared minus V naught squared divided by 2G. I'll just kind of keep going here. Let me circle that off on the side and say Y equals V squared. V was 0 meters per second. 0 meters per second squared minus V naught squared minus 15 meters per second squared divided by 2G, 2 times negative 9.8 meters per second squared. I'm putting that in parentheses as well because you can plug this into your calculator and do 0 squared minus 15 squared divided by 2 times 9.8 and get the wrong answer. And I don't want you to get the wrong answer. So Y equals, in the numerator here, on top of the line, 0 squared is 0, minus 15 squared is negative 225. In the numerator, negative 225. 225 watts meters squared per second squared. That's just the units. Don't worry about that yet. It doesn't make sense. That's not a real unit, but we're not done yet. In the denominator, it's 2 times negative 9.8. That's negative 19.6. Negative 19.6 meters per second squared. So if you ever have fun canceling out units, second squared in the denominator, second squared in the numerator, in the denominator of the numerator and in the denominator of the denominator. Either way, they cancel out. Lone meter here in the denominator, meters squared in the numerator, so that cancels out with one of them. We get meters as our ultimate unit for displacement. That makes sense. So negative 225 negative divided by 19.6 negative is 11.47. I'm going to call that 11.5. 11.5 meters. That is my final answer. So I toss a ball straight up in the air at an initial velocity of 15 meters per second. It will go up and up and up until it starts coming down. And so it went up a total height of 11.5 meters before it turned around and came back down again. Does that make sense? Is
I have
that
a question.
yeah.
So what do we need our calculator in?
Degrees.
Degrees?
Yep.
So when I typed in the bottom one of my calculator, the 2 times the negative 9.8
Yeah.
Squared, I didn't get the 19.6.
So in the numerator, it's 15 meters per second, and then outside the parentheses squared. V squared minus V naught squared. In the denominator, it's 2 times the acceleration due to gravity is 9.8 meters per second squared. It's not, we're not squaring 9.8. We're saying that the unit for acceleration is meters per second squared. And that's an easy mistake to make. So I'm glad you pointed it out. But you're not squaring 9.8. You're just using 9.8 as a value, and the unit for that is meters per second squared.
Okay, I think I accidentally carried over to.
And you know, no trig functions yet, so the degrees and radians wouldn't matter. All right. They're all drawings. And finally, for this set of warm-up questions, I'm going to toss the same ball straight up in the air with the same initial velocity of 15 meters per second. But now I want to know, I'm going to start a stopwatch. The moment I let go of it, it's going to go up, 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 and then come back down again. And miraculously, I'm going to catch it at the same height that I released it. And I'm wondering how much time elapses. How long does that take for me to take a ball, toss it up in the air, and catch it again at the same height that I released it? So what do I got? I got an initial velocity, positive 15 meters per second. I've got the acceleration due to gravity, negative 9.8 meters per second squared. Want to find the time. I need to know at least 3 of my 5 kinematic variables. Do I know another of the kinematic variables? Anyone have any ideas? I will, oh, go ahead.
For the displacement, wouldn't it be 11 and a half times 2 because it's going up and then back down the same distance?
Oh, that is so barking up the right tree. But displacement is the difference between the starting position and the final position. So if by some miracle of coordination that I'm not known for, I caught the ball at the same place that I released it, then the displacement would actually be 0 meters. Because you end up back right where you began. I sometimes make this point when we're talking about displacement that in a typical day, I wake up in the morning in my bed, and then at night I go back to bed, and so my displacement for the day is typically 0. I'm back right where I began. No matter how far I traveled in between, maybe I went somewhere and did something, but my displacement for the day is 0. So the displacement of the ball, if I somehow throw it up and catch it again, would be 0. True enough, we already figured out that the maximum height would be 11.5 meters. So we have some information there, but for the whole event. The other answer that sometimes people give, so we'll fill in that 0 meter displacement right now. The other answer that people sometimes give, and I want to address that now, is the final velocity. The final velocity of the ball is not 0. And I know that that can be frustrating and confusing. If I toss the ball up and I catch it, then when I catch it, the velocity is 0. But in any of these questions, when I ask a question about something going up and coming down again, when we mention final velocity, what I mean is the final velocity, the instant before it hits my hand or the instant before it hits the ground. In terms of a full disclosure of what's going on here, if I take the ball and I throw it up in the air, I have given it some force. I've provided a force to the ball to get it to fly up in the air. And we're starting our analysis after that force concluded, after that force took place. Then again, when the ball's coming back down again, in order to catch it and stop it, I'm providing another force. Force provides acceleration. It's hard to, spoiler alert, there's a lot coming up in physics class. Force equals mass times acceleration. That's probably an equation you've heard. And that acceleration from the force is unaccounted for here. And so we can't apply these equations of kinematics if we have these other accelerations in there. So we're not going to say that the final velocity is 0 because that's not a good final velocity for this round trip. So right now we have 3 knowns, 1 unknown. We would like to figure out what it is. The other thing that we don't know is the very final velocity, but we don't care. We want to find an equation of kinematics that does not have final velocity in it. This one has final velocity. This one has final velocity. This one has final velocity. This is the equation of kinematics that does not have final velocity. X equals V naught T plus 1/2 AT squared. All right, so X is standing in for displacement. 0 equals, our initial velocity was 15 T 1/2 times negative 9.8 is negative 4.9 minus 4.9 t squared. I don't know if you're having a flashback to some math class where maybe you had to solve a quadratic equation. If I was a meaner person, I would have thrown the ball up in the air and not caught it. Therefore, it would have a displacement and we would have a quadratic. But because I caught it, we don't have a quadratic. All we have to do is factor out time. So it's not that bad, but it looks kind of scary. I'm going to divide the entire equation by time and put that t out here. So when I do that, I get 0 equals 15 minus 4.9t times t. So you can see how we could do that backwards, right? If I multiply through, 15 times t is 15t, t times 4.9, t is 4.9t squared. So we just factored out one of the times. What does that mean? Well, this equation has two possible answers. For this equation to be true, for this equation to equal 0, one of the answers is t equals 0 seconds. What does that mean? Well, it means the displacement of the ball at time equals 0 seconds was 0. And I guess that's ultimately what we're asking here. When did the ball have a displacement of 0 meters? It had a displacement at t equals 0 seconds, and then it didn't. Then it was on its way up in the air toward its maximum height and then came back down again. So then it didn't have a displacement of 0 meters until this stuff in parentheses, 15 minus 4.9t equaled 0. So add 4.9t to both sides of the equation. 15 equals 4.9t. Oh, I'm sorry, I'm such a mess. Eraser. And then stop erasing, draw. Oh, it's still on eraser. I hate it when it does that. Click on eraser again? Do I click on draw? Okay. So 15 equals 4.9t. If I add 4.9t to both sides of the equation, I get 15 equals 4.9t, which means t will equal 15 divided by 4.9. That's a 4.9. 15 divided by 4.9 is 3.06 seconds. So when we zipped through talking about how to solve kinematics problems, one of the warnings that we had in there is that some kinematics questions can have two possible answers. Here is one where there's two possible answers. One of them is that t equals 0 seconds. The other one is t equals 3.06 seconds. And we have to figure out which one is relevant to the answer. And since we're asking how much time elapses between it leaving my hand and me catching it back at the same point, then that would be the longer time, the 3.06 seconds. Toss it up in the air, it goes up, and you catch it again. Okay. Let me close these things. find the Canvas page again. I'm getting there. Hold on just a moment. All right. Share screen. We are moving into the world of chapter 3, partly because we have a holiday, and partly because we're just continuing on down the road. When you do problems of kinematics in one dimension, you do the kinematics problem once. When you have problems of kinematics in 2 dimensions, you're going to do that kinematics problem 2 times, one for the x-axis and one for the y-axis. So nothing startlingly new with that foundational skill set that we have developed using these 4 equations of kinematics and our kinematics variables, and asking some question about the motion. How far did it go? How much time did it take to do that? What is its acceleration? Those kind of questions we are still able to explore, but now it's time for a little bit more. So again, calculators, now you want them to be in degrees, not radians, now and always in this course. And we're going to talk about vectors. Vectors have magnitude and direction. The direction is going to be very important to us. So we don't need these pictures. We want to move on to something. All right, so I blazed through some concepts from chapter 1, which included that a triangle is made up of 3 sides. We call these sides A, B, and C, and they are related to each other by this Pythagorean theorem, a squared plus b squared equals c squared, such that if we know 2 of the lengths, A and B, we can figure out the third one, C, which is the hypotenuse, by saying C equals the square root of a squared plus b squared. That will be a useful tool to us on a number of occasions moving forward. So vectors in physics. Scalars are numbers with units. Vectors have magnitude, which is a number with units, and direction. There's a direction associated with it. So if you are standing somewhere and you see someone and you say, hey, could you tell me where the library is? And that person said, oh yeah, the library, no problem. The library is 1/2 mile away from here. That person would not be very helpful now, would they? Because you could travel a 1/2 mile in any direction, and the odds are very unlikely that you're going to wind up to be at the library, right? So if you travel a 1/2 mile north, well, there's no library there. 1/2 mile east, south, is that where the library is? Is it, you know, southwest, northwest? You know, you don't know. You don't know where the library is. You need some more specific directions. So if you ran into that person and they said, oh yeah, the library is a half mile away from here, it's a half mile at, you know, an angle of 45 degrees north of west, well, you can imagine, all right, so what does that mean anyway? So you're going to align yourself facing west and then angle 45 degrees north of west and walk for half a mile. And that might be awkward because you'd be cutting through a bunch of people's yards and they might get grumpy about it. So let's set aside our half mile stuff because I don't have anything organized that way. If every city block is, you know, 500 meters, it's probably big city blocks. Anyways, if every city block is 500 meters, then 1,500 meters, what is this, west? And then 1,500 meters north. And I want to do the vector sum. The vector sum is to figure out what 1,500 meters west plus 1,500 meters north is. It is not 3,000. So sum and vector sum are two different things. What do I want to? I want to do the a squared plus b squared equals c squared thing. C equals the square root of 1,500 meters squared plus 1,500 meters squared. All right, so the resultant vector, the length of the resultant vector, the distance that is represented here, 1,500 squared is a big number. 2.25 million is 1,500 squared plus 1,500 squared. So that's again 2.25 million. So 4.5 million. That sounds a little long for my trip to the library. And then I take the square root of that. Square root of that is 2,121 meters. So the shortest distance between 2 points is a straight line. So even though my walk to the library, if I walked down Birch Street and then banged a right and walked up 2nd Avenue, I travel 3,000 meters, 1,500 plus 1,500. If I took a straight line path, it would have only been 2,121 meters. That's the resultant vector. Also, there's an angle theta. So opposite, adjacent, and the hypotenuse. I know the opposite and adjacent values. Tangent theta equals opposite over adjacent. So theta equals inverse tangent of opposite over adjacent. Theta, the angle theta, inverse tangent of 1,500 divided by 1,500. Theta equals inverse tangent of 1. So in my calculator, I plug in the number 1, I hit second tangent, and I get 45 degrees. Just says 45 on my calculator. I have to know that that means 45 degrees. 2,121 meters, 45 degrees. 45 degrees what? 45 degrees north of west, meaning that I'm going to face west I'm going to angle 45 degrees north of west, and then I'm going to travel for 2,121 meters. This is the resultant vector, or sometimes what we would call the vector sum of these two components of the vector, a squared plus b squared. Okay.
I have a quick question.
Yeah.
Why did you do the tangent, the like -1? Is that because you're going on the negative axis? Like,
No, it's because I know the two lengths of the sides. If I know this, the length of the opposite and the length of the adjacent, then I'm not trying to do tangent, which is a function of some angle. I don't know the angle, so I'm going to do the opposite thing. I want to figure out what the angle is. So, oh, darn it. I'm off of drawing. Let me get back into drawing mode. Tangent theta equals opposite over adjacent. Inverse tangent of opposite over adjacent equals theta. So
oh, okay.
if I know the two lengths of the sides and I want to find the angle, I do the inverse of what tangent does.
Okay.
And stop drawing. Okay. So when we're doing vector addition, I don't know what life in schools have been like for you, but at some point in your math life, you maybe did something with a number line where you took 2 plus 1, 2, 3. 2 plus 3 equals 5. And that's the tail to head method of vector addition before you even knew you were doing any such thing. So if I said vector A equals 3, vector B equals, I guess it's more like 1, 3 plus 1 equals 4. The resultant vector would be 4 in the positive x-axis. And when things are all aligned in the same axis, then we can just do regular vanilla addition. 3 plus 1 equals 4. But if we did the same tail to head method of addition, but things are not aligned in the same axis, so vector A is 3 meters east, or in the positive x-axis, but east works. And vector B is 1 meter north. Then 3 plus 1 does not equal 4. We do the a squared plus b squared equals c squared. The resultant vector is going to be c equals the square root of a squared, 3 squared plus 1 squared. 3 squared plus 1 squared is 10. And the square root of that is 3.16. That tells me the magnitude. The vector is 3.16 meters long. It doesn't tell me the direction. Just looking at it, I can tell that it's north of east, but my skill set is not so developed that I could tell you what angle it is. I think it's less than 45 and more than 20. Maybe I'm wrong about that even. But I know the opposite side and the adjacent side. So again, we'll do that same tangent thing. It's not always the way we do it, but So tangent theta equals opposite over adjacent. Theta equals inverse tangent of opposite, that's 1, divided by adjacent, that's 3. The units cancel out. I don't need to worry about meters. It's just 1 divided by 3. 1 divided by 3 is 0.333 infinity. Inverse tangent, I get 18.4 degrees. So did I say it was more than 20? I was wrong. 18.4 degrees. That's not the answer yet. 3.16 meters, 18.4 degrees. I also have to specify that it's north of east. And what that means is I'm going to face east, and then I'm going to angle 18.4 degrees north of east. So I'm going to face east and then angle north of that. And if I did that and was at 18.4 degrees and I went out for 3.16 meters, I would end up at the same finish point as if I walked 3 meters east and 1 meter north. Vector addition. It is not so bad. It's just a little bit different than what we do other times in our lives.
I have a question.
Yeah,
So if we're like trying to type in the degree as the answer, for example, do we need the units like the NOE?
yes.
Okay, so do
North
we
of east, north of west, because it could be other things, right?
yeah.
So I need to know, which direction we're going.
Okay,
Yeah.
so just to clarify, we type in as NOE or N of E.
N of E.
N of E, okay.
Yep. To find the magnitude of a vector, you use the Pythagorean theorem. To find the angle in degrees, you use one of the trig functions. It's not always tangent, but it kind of feels that way. And then to find the compass reference, north of east, north of west, south of west, to find the compass reference, you kind of have to step in and just use logic after that point. So there's like three tools we have in our toolbox here for doing vector addition. All right. So just along those ideas, so north, south, west, and east. We have our compass, 100 meters, 30 degrees north of east. So I'm going to face east. I'm going to angle 30 degrees north of east, and I'm going to draw a vector that I'm defining as 100 meters long. All right, 100 meters, 30 degrees south of west. So now I'm going to face west. I'm going to angle 30 degrees south of west. And I'm going to draw a vector that is 100 meters long. 50 meters, 30 degrees south of west. Well, face west, angle 30, but now it's only 50 meters long. 100 meters, 60 degrees east of north. We don't usually do things that way. So I'm going to face north, and then I'm going to angle 60 degrees, and I'm going to draw a vector that is 100 meters long. And I will discover that vectors A and D, I think I have a cheesy, they're in love with each other. So vectors A and D are the same here. and it matters the order that you do things. So usually we will have the last word be the east or west reference. So we would say north of east or south of west, that kind of thing. And then the vector magnitude and direction. And direction is not just the degree, the angle with degrees, it also has to have the compass reference to make sense. Clear all drawings, okay. We don't need to do the checker triple jump. Let's do the tree observation because that's a decent one to look at. So we have an observer. They're standing out here. For reasons that aren't entirely clear yet, they're letting us know that their eyeballs are 1.83 meters above the ground. And 32 meters away from where they're standing, 32 meters, my apologies for not being able to draw a straight line. There's a tree, the tree is growing up, kind of a Dr. Seuss tree. The tree is growing up out of the ground, and it turns out that the line of sight of our observer's eyeballs is making an angle of 20 degrees above horizontal. And so we want to know how tall this tree is. So we have a value for adjacent. So any triangle has hypotenuse, opposite, and adjacent. We have a value for the adjacent. It's 32 meters. 32 meters, level ground, tree is growing perpendicular to the ground. We have adjacent, we have an angle theta, and we're looking for the opposite value. We want to find the height of the tree. So given that information, opposite and adjacent, we are back to tangent again. Tangent theta equals opposite over adjacent. This time we want to find what the opposite value is. So we're going to say opposite equals adjacent times tan theta. The opposite side, the height of the tree above the guy's eyeballs, is going to be adjacent 32 meters times tangent of 20 degrees. Again, this is the chance to plug 20 tangent into your calculator. However you do it, I don't have the TI-80 something here with me, but if you have one of those, then you typically press the tangent button and then parentheses appear and you do 20 and then you close the parentheses and hit equals. On my TI-30X, I do 20 and then the tan button in order to get 0.3639. 0.3, oh no, I hit a button, 3639702, whatever, but that's what tangent of 20 degrees is, and then times 32 is 11.64. Opposite equals 11.64 meters. That's the height of the tree, 11.64 above the guy's eyeballs, 1.83 meters. So I then have to add in the eyeball height, 1.83, to get the total height of the tree, plus 1.83 of 13.5 meters. It's the total height of the tree. All right. Hold up 1 second. Okay. Clear all drawings, close. All right. So here is the world of two-dimensional kinematics. So why we were talking about vector addition and vector sums is because when we have a world of kinematics in one dimension, it's a little bit like I have my rocket ship where I press the button for the x-axis booster rocket and my rocket moves in the x-axis. Or maybe I'm going to push the button for the y-axis booster rocket all by itself, and my rocket will move in the y-axis only. But wait, what if I press both buttons at the same time? If I press both buttons at the same time, then I will have x-axis motion and y-axis motion taking place at the same time, but they might have different accelerations. So maybe this seems a little otherworldly, but closer to home here on Earth, if you take a ball and you throw it in the positive x-axis, which is just kind of throw it in front of you, it has both x-axis motion and y-axis motion. In the y-axis, it tends to be accelerated down toward the surface of the Earth. That's the acceleration due to gravity. In the x-axis, there is some air resistance, but that is negligible compared to gravity, such that we essentially have two motions, x-axis motion and y-axis motion, taking place at the exact same time with different rules. For the y-axis, we have the acceleration due to gravity pulling it down toward the ground with an acceleration of 9.8 meters per second squared. In the x-axis, it just wants to keep going, just wants to keep flying through the air. So we have to deal with those two things taking place simultaneously, and we will have some work with vectors in order to do that. We don't need to do that example. There's this world of relativity, relative motion. This is the foundation for Einstein's theory of relativity. This idea, and this is also vector addition, that if you are on a train that is moving in the positive x-axis at 15 meters per second, but you are walking on that train also in the positive x-axis, you would actually be moving, according to an outside observer, according to this dude standing on the ground, you would be moving forward at 15 plus 1.2, 16.2 meters per second in the positive x-axis. Whereas if you are walking the opposite direction of the motion of the train, then it would be 15 minus 1.2. I think the, if you ever go into like Logan Airport and are going from the parking garage to one of the terminals, they have the moving sidewalk thing. That's the whole gist of it right there, right? Like, you know, you're there at some time of day and you are on the moving sidewalk, but you turn around and face the other direction and walk in the opposite direction at the same velocity of the sidewalk, and you're essentially standing still. You can imagine that, right? If you haven't done it yourself, you're able to achieve an actual velocity of 0 because the sidewalk's moving forward, but you're walking backwards and you can achieve this velocity where you're standing still. Or if you're like a normal commuter person and you're in some kind of rush, the sidewalk's moving forward and you're walking forward and you're actually traveling faster than you would have been if you were just walking all by yourself. That's relative motion, relative to a stationary ground-based observer. You have changed your velocity. You could also do that, maybe not on the moving sidewalk at Logan Airport, but if you climbed up. So if the train is moving forward, but you are moving up, then we have the velocity of the train relative to the ground, the velocity of the person relative to the train, and then the vector sum would be the velocity of the person relative to the ground. And that would be at an angle. And what we would have is something that would look like, to our stationary ground-based observer, as though the person were moving up like so. So the velocity of the person relative to the ground, you would watch them and see them moving up at some angle. Not going to have a ton of stuff on this, but I just want you to be aware of the concepts of relative motion. All right. Coming up soon, we're going to be putting pieces of this all together into this idea of projectile motion. So the airplane is delivering a care package to the people on the ground below. The airplane is moving at 115 meters per second in the positive x-axis. It releases the package. The package is falling down to the ground. It's still moving in the x-axis at 115 meters per second the whole time. But in the y-axis, VOY, when it's released from rest, its initial y-axis velocity is 0, but it is subject to the acceleration due to gravity in the y-axis, negative 9.8 meters per second squared. So it's going to accelerate down toward the ground faster and faster in the y-axis. And we want to know its final velocity and angle. Final velocity in the y-axis is not 0. Vy final. Not 0. We want to know the y-axis velocity the instant before it hits the ground, and then use that together with the x-axis velocity to find its real final velocity at some angle. So we separate out x-axis motion and y-axis motion. In the x-axis, it's kind of boring because it's just going to keep moving at 115 meters per second forever. In the y-axis, known and unknown. In the y-axis, we have an initial velocity in the y-axis of 0 meters per second. It was released from rest. We have the acceleration due to gravity, negative 9.8 meters per second squared. And we have a y-axis displacement. Again, this word displacement is different from distance. Displacement has a direction associated with it. Its final position in the y-axis was 0 meters. Its initial position was 1,050 meters up in the air. So its displacement is negative 1,050. It fell down. I want to know what the final velocity is, knowing that it's not 0. And I don't know anything about the time, but I don't think I care. So only one of our equations of kinematics doesn't have time in it. We do the v squared equals v naught squared plus 2gy equation. Life is a little bit easier now with this equation because we're looking for v. So v equals the square root of 0 squared plus 2 times negative 9.8 meters per second squared times negative 1050 meters. V equals 2 times negative 9.8 times negative 1050, square root of that, 143 meters per second. I am so sorry to spring this on you at this stage where your brain might be a little bit fried, but final velocity of 143 meters per second, like that's what showed up on my calculator, but that's not the answer. The square root of anything, the square root of 4 is plus or minus 2. Whenever we take the square root of something, we have to accept that there's two possible results. What times what equals 4? Well, 2 times 2 equals 4, but negative 2 times negative 2 also equals positive 4. So this answer is plus or minus 143 meters per second, and in reality, it's negative 143 meters per second. The final velocity of the package that fell down and was accelerated by the acceleration due to gravity, the final velocity, the instant before it hits the ground, is going to be negative 143 meters per second. So now, vector sum, we have x-axis 115 meters per second, y-axis negative 143 meters per second. We want to find out the magnitude of the actual final velocity and then the angle into the ground. The magnitude, a squared plus b squared equals c squared. So the negative 143 kind of doesn't matter anymore because we're squaring it. A squared plus b squared equals c squared. So 115 squared plus 143 squared, square root of that number is 184 meters per second. That's the speed of this package as it comes crashing down to the ground. Probably could have used a parachute or something. And then the angle theta, opposite over adjacent, inverse tangent of opposite, 143 divided by adjacent, 115. I'm doing away with the negative sign right there because we'll get a different angle if we do it the other way. 143 divided by 115, inverse tangent, I get 51 degrees. What is that? Below the x-axis, south of east, however I want to phrase that appropriate for the problem. So I could just say 51 degrees south of east, and that would describe this angle that is below the x-axis, but still in the positive positive x-axis. Ooh, okay. Let me clear. If you were on a train going up a flight of stairs to the upper level, then your velocity would be presumably something like at a 45-degree angle. And so you'd have more complex vector addition because you'd have a 45-degree angle and a x-axis velocity, and you'd be adding those together. I respond every now and then to private chat questions, but if other people are thinking the same thing, I figure that's good to hear. The next thing we have to do, I don't know if you've heard stories of me from other people, but if you have heard any stories of me, you have likely, oh, where did it go? It's got to be here. You've likely heard of how crazy I am about the football question. And the football question is the next thing we have. And I'm going to save that for a fresh start for Wednesday. We have covered everything that will be on the quiz next Wednesday and gone a little bit further than that even. And I don't even know where the football question is, so I will find it. So I think we're good. So for those of you who are like, wait, what's going on? Why, you know, time and whatever. Let me share. We're in okay shape right now. So what I'm looking for you to do between now and next time is take a solid whack at all of the chapters 1 and 2 homework questions. And, you know, sorry, there are a bunch of them. If you're struggling with any of them, you click on the homework video question and summon me to your side to walk you through the question. And then I want you to take a whack at the lab. Lab number 1, I have directions here. You can write out your answers on just a piece of paper and then take a picture of that piece of paper and upload it for your answers here, a text entry box or a file upload. So if you want to type it all in as text entry, that's fine. If you find it easier to write it out on a piece of paper and then take a picture of that piece of paper, that works as well. If you have questions between now and next time, go ahead and let me know. And otherwise, that's it for today. Monday's a holiday, and then next Wednesday, we'll cover some more material. We'll do the football question, and we will have a quiz, and then keep moving ahead. So that's enough for today. I will post the video. Just takes a while to download and process. So if you're looking for it right away, it doesn't appear right away. Anything else before we go? All right, have a happy day, have a happy weekend. I will see you on Wednesday.
Thank you. Have a good day.